So let us go through an example of a higher order Lagrange polynomial. This particular example, 613, is a fourth order polynomial in Lagrange form. They give us some data, but first let's do an expansion of just the Lagrange form itself. So we are given the summation from I equals 1 to n of y sub I multiplied by the product sum j equals 1 when j not equals I to n. Now that's not imaginary I, that is the index I. So x minus xj divided by x of I minus x of j is what's contained inside that product sum. And this, of course, all equals f of x. All right. So to expand this out, we have f of x equals y of x. And then we will start with just the summation from y, or I equals 1 to n of y sub I. Draw the dot. So this would be y1. Now we're going to take, this example takes everything inside the red brackets and calls that Lagrange of n. So let's change back to color. We'll call this Lagrange portion 1 plus y2 L2 plus y3 L3 plus y4 L4 plus y5 L5. So that will encompass all the terms we need. Fourth order polynomial in this case will take 5 particular points that it passes through. So in each case, for each one of these L's, we have to determine what is inside the red brackets to define L1, L2, L3, L4, L5. This is where some of the tedium sets in, but if you really understand the process, once you start doing this, it's very easy. Very little calculation is involved, but certainly, I should say very little calculation is involved in the setup, but then multiplication is involved in determining the answer. So let's look here. So when for L1, we would have I equal to 1. So this means that we skip the very first j. So we start at j equals 1, but we skip, by definition, the point where j is equivalent to I. So we have to immediately move to j equals 2. So the j2 term of this product sum would be x minus x2 divided by x of I, which would be 1, minus x of j, x2. Okay. j3 term, x minus x3 divided by x1 minus x3, j4 term, and this just keeps going. j5 term. All right. So that sums things up there, except whenever we're given a set of data, we'll actually be able to go in and populate everything, x1, x2, x3, all the different x values, and come up with actual coefficients. In this case, just to fill things in, this L1 term ends up becoming x minus 22 times x minus 30, x minus 38, x minus 46, all divided by 98,304. So that would be the last form of the L1 term. Now, unfortunately, I have to remind you that this is only L1. This formula has to be gone through 4 other times, L2, L3, L4, L5, in different forms until you finally have all of the solutions necessary to finish things up. So if we were going to look at this in its full form, shuffling papers around, that is what we're looking at. So notice it is the A1 coefficient, the Y1, multiplied by L1, which you just figured out. Remember, you recognize the denominator. Minus, in fact, it just happens that the The L2 term is negative, so y2 times the negative L2 term, L3, L4, L5, all multiplied by their respective y's, ends up coming out to be the definition. Notice there's only one variable remaining, x. When you plug in the x value you're interested in this case 26 miles per hour, you obtain the output of interest. So in this case, the output of interest, as my camera readjusts, is 530. For the x velocity of 26 miles per hour, you obtain a power output of 530 watts, because I believe this is posed as a windmill type problem. So that is what a Lagrange polynomial of the fourth order looks like. It's a lot of determining L1, L2, L3, L4, L5. This can be done numerically, of course, to put all these coefficients in the right spot. It makes interpolation between those points rather straightforward and simple.